Can you hear me? Doesn't seem to. Does it work? Yeah. All right. That's good. Okay. Looks good.
All right. Welcome back. Welcome to day 2 of the useR 2025. It's my pleasure today to introduce our next keynote this morning, Simon Urbanek. Simon is an associate professor at the University of Auckland. Before that, he was a former AT&T Research Lab scientist for 15 years. He is perhaps best known in this community as a R core team member, I think maintaining R for Mac OS. So if you have a Mac in the audience, come up and thank Simon afterwards. He is an expert in distributed computing, visualization, and big data analytics. And this is, I think, an important and exciting perspective. Today, he's going to talk about how R has adapted to the AI era. So I think there's going to be some interesting perspective transitioning from R in the era of big data to R in the era of AI. We've heard a little bit about AI already at this conference. He'll be telling us about fitting, evaluating attention models, leveraging LLMs for analysis and retrieval. So with that, please join me in welcoming Simon to the stage.
Thank you, Matt. So thanks, everybody. Thanks for having me here. The idea for this talk essentially came about partially with the question that was asked yesterday at the end of Hadley's talk, which is, now in the AI era, when things, people are using Python a lot and so on, are we going to get our lunch eaten? And my answer is, well, there's actually good reasons why we use R, and R is not limited to particular technologies. And this is sort of kind of the point I want to make here. So I will be going through a couple examples where we're using R for some use cases. And bear with me, they don't start with AI, but I promise they will sort of get into that world. And the other aspect is that it's not about AI the way Hadley talked about yesterday, which is great, and it's something we all want to use. But I also want to get into the idea of, well, we should also be looking at the technologies behind AI and maybe using those, incorporating them in our analyses. So it's not just using AI for the coding aspects or even the agentic ones, which are great, but it's sort of different lens that I want to look at. And this work has been a collaboration with Mike Kane. You may know Mike from the big memory package, big regression, and so all the big packages. So now he's also moving from the big data era to the AI era. So that's where we want to go. So a rough overview, what I have in mind here is that first I want to talk a little bit about R as a data analytic language. And that is sort of a very important distinction I want to make. So a little bit of history, some key design aspects. Then I'll still stay in the big data era in some sense. I want to talk a little bit about just data sizes and speed, but I'll only spend very short time on that. And then I want to talk about R as essentially a conductor or like conductor of an orchestra. So you're just essentially trying to use tools, methodologies in the context of data analysis. And I will do that with two use cases. So one is what we call the New Zealand journey to work data. So it's essentially census data for where people live, where people work. And we did some analysis of commute, safety, and other things. So I want to talk about that, which leads to an attention model I want to talk about. And then another use case is using our journal articles and using embeddings as sort of one of the ideas there. So this is sort of what I'm planning here. And throughout this, I'm using these essentially to illustrate my point, what I think the strength of R are, and how we can use it and why we want to use it that way. So R essentially is based on the S language, which is more than 50 years old now. But the main goal of S was to have an interactive interface to Fortran routines. So that's how it worked way back then. All you got was Fortran code, so you didn't want to code Fortran in order to do data analysis. So that's why the key aspect was for it to be interactive. So we wanted to interact with data, and we just wanted to use tools like Fortran code to essentially allow us to do the analyses that we wanted. And of course, that was all we had back then. And then R came about and added a couple things to it. So one is, it's a vectorized language, which means there is essentially no such thing as a scalar. Everything is a vector. So all operations are defined and optimized for vector operations. So matrices and vectors are sort of the basic building blocks of the entire system. And that means those are inherently fast, unlike in other languages where they don't have a concept of a vector as a native object. And of course, very important, because of the fact that R can be inherently extended with packages, that allows us to interface not only just with R code, but also with pretty much arbitrarily any native code. So it doesn't matter what language it is in. We have, of course, some built-in support, but you can expand it with other languages as well. So first, a little bit aspect I want to talk about is scaling R. So we're thinking of R as essentially the orchestrator. So as long as you use it that way, it's actually really fast because you're simply delegating the real work to something that's either in native code or in some other tool and so on. And that means, if you work, you want to make sure that you're really leveraging the vector aspect. Now, this is the hardest thing for anyone who comes from another language, because if you're used to programming languages, so I'm making the distinction here as R being the data analytic language, which is also why we have things like partial matching of arguments, right? You wouldn't need that in a programming language, but you kind of want that in the data analytic language because you're just interacting with the tools. You're not really programming per se. So if people come from other languages, they're used to things like, oh, I need to handle every single element this way. No, we just write out formulas pretty much the way they're expressed in maths, and they actually just work in R, which is, if someone else comes to R, they're kind of really surprised that you can just write out a math formula and it works on vectors and everything is fine. So if you want to scale R, the best way is try to use these facilities. Now, of course, everyone complains, oh, R is slow, everything has to fit in memory, which is true. Now, notwithstanding the fact that you can have now, 1 terabyte memory machines that are not that expensive anymore. You don't need millions of dollars to buy them. Still, you can work around it by simply saying, well, I can split things into chunks, and I mean chunks, not individual rows. So this is, way different. And the nice thing about that is because we know how to deal with entire matrices and data frames. So if we just create smaller ones and then combine them, then we actually solve the problem and still leveraging the speed that we have in R. So I just want to give you a quick example. And the reason I'm showing this example, not because this is explicitly what you want to write, but sort of just to show you the power that we get in R for free, so to speak. So let's say I have a data set that has some shapefile, or is a shapefile, essentially polygons. In this case, I'm looking at, let's say, zip codes. And I just want to take a data set that has latitude and longitude, and I want to map it and just get, where are these points? And then count them within each zip code. So this is all you need in R, right? So all we need to do, we need just a function that will do sort of point polygon matching. That gives us the index of the record that matched. So it's sort of like match for a spatial match. Then we just subset our zip code, so we know which zip codes this is. And then we just run table. So it's that simple. It's one line to essentially do this entire process. And it's all vectorized because we're dealing with all of them at once. We're processing the entire data set at once. Now, if the data set is too big, let's say it lives in a distributed system because it's just way too big to store it locally, and we can do parallelization, all we need to do, essentially, we can split it into chunks, and then we do exactly the same thing for each chunk. So essentially, that gives us the distribution of zip codes for each of the chunks that we processed. And the only additional step we need to do is we have to count up the results at the end. So the only thing that we have to think about, well, if I can do it partially in each one of them, how do I combine them together? So this is just one way. We just only need to pretty much match up all the same zip codes from all the chunks. So the reason why I'm showing this, because that means essentially we are not changing this code, because we already wrote the code to be essentially vector aware or work at the entire data set at once. And so that way, we actually don't have to change anything. If you were to writing it sort of row by row, or you have to sort of now combine and do things, and it would look differently. So this is what the result then looks like. Let's say if you want to use the Hadoop MapReduce package, let's say the data was stored in Hadoop, just as an example. All you need to do, you're literally just putting these two, I should put in a function here, but in these two calls pretty much in the call, and you're done. And then we just can ship whatever we need to have inside with the call so that that gets distributed as well. So that's what the point I'm trying to make here, that in R, we're really expressing what we want to do, and it's very concise and intuitive. At least, for us statisticians, if coming from the background where we think of things in a sort of mathematical way. So we don't really worry too much about how. We typically try to leverage sort of existing tools that are there. The other two aspects is, so interactivity is really important, right? So because we're dealing with data, we want to interact with the data. It's not static. We don't know a priori what we're trying to do. So it's not like programming languages where you essentially more or less have a spec and you're saying, oh, this is what I want, and you just code it up. No, we're just dealing with the data. We have some idea what we're trying to do, but as we're looking at the results, that really determines what we will do next. And that's why it has to be interactive. And also, graphics comes into play as well, because as we're looking at the data, we want to draw it, we want to plot it. So, because that will be informing our next steps. So that's why it's so important, this interactivity aspect of it. And finally, the generic language, meaning the fact that we have a function that says plot, we have a function that says print, we can function that says predict. So these are generic functions, meaning they will change behavior depending on what you give them. And that's, again, sort of a very natural thing to do when we're analyzing data, because maybe we use one model, and then we say, oh, let's try another one. We don't want to be rewriting code and changing names of the classes we're using or anything like that. We just want to say, that's what we want to do. So again, this is something that R is really good at, because that's sort of been designed this way to be a data analytic language and not a programming language. So the first use case I want to talk about, I'm going to just introduce the data a little bit. And the idea was that we have this, so in every census in New Zealand, we have a question that says, where do you live and where do you work? And those two locations essentially get aggregated at sort of a higher level and then are part of the census. So with that, what it means is that we can do something with respect to understanding commutes. So where do people commute from? Where do people commute to? Which areas are affected by the traffic? What are the volumes on streets? Are there any risks along the way? And in general, it's kind of I want to sort of use it as an example of sort of wider concept of human mobility, because we can, if you have any kind of data set along those lines, then how can you track sort of the movement of people? So in this case, we're going to be estimating the commuting routes based on this information. So we only have the two endpoints, sort of in a rough way. And then, so we want to sort of figure out where are people going. And then we want to create a graph on which we will then work later on. And that's where our further models come into play. So the data set, as I was saying, is the 2018 census. We didn't get the so it's every 5 years. The 2023 census, we still didn't get the data from, so it was 2018. And we have these areas which are called statistical areas, which are essentially aggregations that are sort of roughly designed to have roughly constant population, so they expand in the rural areas, are much smaller in cities. And so we have these pairs where we have the work and the home, SA2 and then we have the count. So how many people live here and work here. We have all different means of transport. So things like, are they the driver, are they the passenger, are taking public transport, are they cycling or walking? So in this, just for the illustration purposes, we'll be using essentially the driving part of it, but the information is there. And there's this little bit of censoring, so if it's just one person driving here and living here, they don't report that because kind of easy to identify who that person is. So this is what the data sort of looks like. So I have just 2 SA2s, and this is sort of further up in the North Island. So we have a really rural area, so that's big, and then we have a small town that's actually much smaller. And so what we do is, how can we figure out how are people going from that home to that work? Well, one easy way is just saying, let's take the centroids and just use a routing software to figure out how do you get from A to B. So that's what we'll start with, and then I'll talk about some improvements we can do on that. But let's say we start with that. So how do you want to do that? Well, it's actually really easy in R. So the first half of the screen is actually just reprojecting because the data comes in this geodetic system that is in meters, and the routing software expects latitude and longitude, so we just reproject. We just put it together as pairs because we want to route from this pair to this pair. Now here is the key that I was talking about. We really want to make it as a one big matrix, so we don't want to be calling the system one by one, which also means we don't want to be using any kind of APIs. We just want to embed the routing software into R because that's so much faster, because that way we can actually do it a lot faster. So we have our matrix here, and then what we do is just load the data from OpenStreetMaps. So I just take the New Zealand subset of the data. You could use the full one, but it's kind of wasteful because we don't use the rest. And then all you need to do is just say route. You give it a pairs. In this case, so this is the GH route package, which essentially under the hood uses GraphHopper, which normally you may know more like an API system, but it actually, because it's Java code, you can actually call directly the underlying routines from R. And that also means you can actually do it using threads, because in Java you can tell it, oh fine, let's say 32 threads, which makes it super fast. So the whole thing takes about 3 seconds. For the, what did we have, something like 50,000 routes that we have in the data. So it's really, really fast, and that will become important later. But the key here is that you really want to sort of work on the whole thing at once, because that makes it much easier to do and parallelized. You don't want to be going through, like OpenStreet's API or anything like that. So this is what it looks like if you do that. So we have all the routes, and this is not that you would actually see the individual routes, but just to make a point that this is really just the whole country in 3 seconds. There are about 7 million points actually that the routes come up with. And the nice thing is then you can essentially do things like estimate traffic. So this is the traffic in Auckland. So this is central Auckland here, and this is the Auckland Isthmus. As you can imagine, traffic in Auckland is a nightmare because, as you can see, there's all these narrow things that everyone has to pass through because there is no choice, right? It's water all over. So this is what it looks like. So what can we do with this? So for example, we can do basic things like, we can estimate the traffic. We can estimate how far are people actually driving, because maybe they have to sort of drive around before they get to the destination and so on. We can also combine it easily with new data, because we're in R. That means, now we have this data set. We can just join it with any other data set. And there are, great packages like SF that allow you to do things like, okay, what's the closest route for a particular point, and things like that. So back to this view. So what we can do is, let's say we just add all the data from our crash analytics system. So it's another system that reports whenever there is a crash, an accident. It reports the severity, whether it involved pedestrians or cars and things like that. So now you can actually go back and just join this data with the routes, which brings it back to the endpoints that we're talking about, right? So we know now if you're commuting from this area, are you really passing through areas that are really prone to high-risk crashes and things like that. So it's really easy to do. So that means we tie the location of the crash to the routes. That means we can compute risks. We can compute the risks based on location. So for example, we can join it with demographics data. Let's say there is a sort of what we call the deprivation index, that essentially for each SA2 we have the score that says sort of how, what's the, essentially what's the, income or sort of on more broader terms, what's the situation in that respect. So that when sort of more deprived regions typically tend to be outside, which means they have a higher risk, and we want to improve that, so things like that. So we can improve these things. There's one little thing that I said in the beginning. We've been just using the centroids. So what does it mean? Well, so for example, if you take my commute, so I live in Mission Bay and the university is in the middle of Auckland, it picks this route. Now, truth be told, like all the buses and everything actually runs up on the Tamaki Drive there up north, which actually does not show up here. So what can we do? What we can do is we can simply sample the points from the region. And now, in this case, I'm just sampling 1,000 points. But you could sample based, let's say, on the number of people you have in each, how that the system reports are coming from this location to this location. And you could even weight it by dwellings, because there's more information on that. So if you do that, then you get something like this. So now you see actually we do have a good portion of the traffic coming down the waterfront here. And so that allows me to actually make it a little more realistic in the sense that I'm not just relying on one single route here. I can actually have a better idea of roughly where we think people are. And the reason why we can do it, again, is because it's fast, because we can do something like 100,000 routes per second, which means that we can actually do things like simulate the whole country with this because it's so fast. So far, we've been just talking about routes. But we want to simplify things a little bit, and we want to go from these sort of maybe unwieldy routes along the roads, which are fine if you're looking for fine-grained information. But we want to sort of have the big picture. So we want a graph where we take the nodes as locations and then flows between the locations. So essentially, we want to partition the space into areas. Well, that's already happened. We had the SA2s. And now we just want to compute the flow, so how many people go from this area to this area. Because with the graph, there's some good things we can do. I didn't go there. Which are, it's aggregating more, meaning we can avoid privacy issues. So it's much easier to export that kind of information. And also that means, we can work more easily on the graph than we can on individual routes. And by aggregating them, we also don't worry that much about the uncertainty. Did you take this street or did you take this street? So how we do that? So we get so this was the route we were looking at in the beginning. So what we can do is let's look at the other areas along the way. And then again, with the SF package, we can just do a little boundary around the route, do an intersection with all the areas. So now we have the areas. These are the different IDs, let's say. And so we can see which pieces of the route go through which area. There's little issues here. So for example, you will see sometimes we are running along the boundary. So what we do is we're essentially saying, well, as long as you don't leave, we still try to keep you on the same in the same SA2. So if they just touched another area, we just carry on and don't include it. But the moment you cross inside, then we start counting it. Again, it's reasonably easy to do in R. And then in the end, that gives us the sequence. So every node is one of these circles. So these are the other, which I didn't show the borders for. But here are the centers of the areas we have here. And we just use it as a graph where each of these nodes is one of the SA2s, and the edges are the number of commuters that went through that way. So if we do that, what happens is actually the North Island is beautifully connected. So as you can see, pretty much it's one big component. In the South Island, there's fewer people, less connection. So actually it does separate. So for example, the blue area here is Christchurch, which is the second biggest city. So that makes sense. But I was kind of surprised that actually it's really one big component that we're talking about in the North Island. I want to talk about, so these are sort of, so these are just the base distributions of where people live. And this is, and with yellow being, it's a heat map, so yellow is the high, red is the low. And this is where people work. So you see it's almost the opposite, which makes sense because people concentrate to work and they spread out where they live. And in Auckland in particular, because of the zoning rules, there is a limit on the height, or used to be, a limit on the height of buildings. So that means it has to spread out because they didn't Originally didn't want high-density buildings. Now that's changed because we can't cope with it. But this is what the flows look like. So this is just looking at each node. So each one is one of the areas. And it's the number of people that coming in. And they will be coming out eventually, but it's just counting as they passing through. And you can see sort of really nicely if I was to overlay the roads, that these are sort of the very main corridors through which people actually commute. So back to the commute view. If we go from that to the flows, it looks like this. So the graph is a priori, doesn't have spatial information, but we know that where the nodes are, so we can essentially draw them. Now, one thing I want to point out here, so the way this is created is, we can have two directions, right? So in the previous view, we just had the road, but now we actually have different way, people coming one way or possibly the other way. So the way we try to display it here is that the red ones are the ones coming, is the larger flow. So in theory, if everyone was going in the same direction, you should be only seeing red in this picture. Now, if there are people coming the other way, you will see blue, that's sort of the other direction, so there will be traffic in both directions. And as you can see, there is some, so this is this is the harbor bridge, so it's the pretty much only way to get north-south. And you can see that the blue is almost as thick as the red, so that means there's actually people going in both directions. So yeah, it's not convenient. People don't actually work where they live. They work there, they live there. Other people live here and work there. So we have this sort of cross traffic. But this allows us to sort of show, what's going on and where are the different areas that we have, counter traffic as well. So why do we want to work with what we call the mobility graph? So this is quite generalizable, all right? So all these methods actually work on any kind of graph that you create. Whether it's some location data you have that you're collecting where people move, it doesn't matter. And it kind of is a good way to do sort of privacy preserving mapping of human mobility, because then you don't have to worry about exposing individuals' data. So some of the work we've been doing with this, we did, for example, pollution exposure. It's sort of how much do people actually get exposed to pollution, or how do infectious disease spread? Things like that. So it's kind of interesting to use that. So with this, now I'm getting slowly to the AI part of the talk. So given the sequence of locations, let's say you wanted to predict where people will actually go. So you can start with, let's say, just one location and say, okay, so if I'm here, where will people go from here? So let's get a set of, let's say, 3 locations. So we say, all right, so you've been through these 3 points. Now, where are you going next? Now, obviously, spatially, we know it's a subset and so on, but let's not worry about it for a moment. But that means we can predict it. So let's predict that. So we get the next location. Now, once we're there, we can say, well, we could predict the next location given now these 4, and we get the 5th, and so on. And if you think about it, that sounds familiar, right? So that's exactly what the LLMs do. Essentially, you start with something, and they just predict the next word, and then the next word, and then the next word, and so on. So why not use the same concept in this context? And you could start with just one. So the idea is, let's use the attention, famous paper, attention is all you need. So maybe that's all we need, right? So let's try that. So instead of using words, we'll be using these locations on the graph as words. Now that means we actually get rid of the entire graph in some sense, because we're not giving it any spatial information at all. We'll be just using literally this node, another node. So we will use these nodes as words. So a priori, we don't even tell the model that these nodes have anything to do with each other, which is important. So here is the attention model. So this is the basic formulation. So you may remember, essentially, we have 3 parts. So this is the query part. So that's the WQ. XI is essentially if we're looking at the location I. So we just start with a matrix that's essentially, so given we have trajectory of length n, so that's how long we go. P is the number of locations, so essentially how many nodes we have in the graph. And so then we just have a matrix, which is one hot encoded representation of the sequence. So, and you can, which way around you do it, whether you start with 1 and end with P or vice versa, doesn't really matter. And then, so this is exactly like using the words, because at the ith word, in our case, ith location, this is the query part, this is the key part, so we're using x again as in the key. And then this is the value part, which we're using, again, x with the value matrix. And then we're just estimating these three matrices. And this is softmax, is row-wise. And then, so that will be our attention. And we just need one more step, which is essentially from the attention, we have one more layer where we just estimating one more matrix and a vector that will be then the actual prediction of the location. So what will this give us, what this will give us, because of the softmax, it means we essentially get a distribution of, in some sense, what are the probabilities of going to any of those locations, right? So it's, because it always sum up to 1, it's a softmax. So that means we essentially can treat them as probabilities of going to the next location. So if we're doing prediction, we just pick the one with the highest probability. And so this is what a training looks like. So firstly, we have to define n. So in this case, we just decided, let's pick 20, because it's sort of long enough that we have, you can think of the n as the context window. So essentially, how many locations can the system, can the model see at a given time? So 20 seemed enough to be meaningful for having enough data to sort of trace through the trajectory, and not being too high, so the model doesn't get too big. So this is what the actual training looks like. So what we do is there are two more things we have to think about. So one thing is, because we want to predict, let's say we have one location and want to predict just the next one. So the way we encode the fact that this is the only location is that essentially we make it the last one, and we just set all the other ones to 0. So in the matrix, there will be just zeros, and there will be only one column with a 1 in it. And then y is our response, is essentially the next location that we're looking at. The same thing, which is just vector with 1, 1 in it, which will be at this particular location. So I'm showing you so before the hot one encoding. So these are essentially the IDs of the nodes. So you can think of it as like an index into the node array. So we just do one location, one prediction, two locations, the next prediction. So we're just shifting this by 1. So you can see the trajectory is kind of moving left as we go. So this is the actual trajectory that we had from the original data. So it was someone going from here to here through these nodes. And then there's one more thing we have to think about, which is, well, we actually want the model to also predict if the person stopped there, if it's the end point of the trajectory. So the way we do that we just keep repeating the last value over and over again. So that way it sort of says, no, you didn't go anywhere else. You just stayed in here. So we're allowing the model to essentially stay at the same location. So this is what the training data looks like. Like you may note, we're not giving it even connectivity information. We're not giving it locations, lat longs, nothing, right? So this is literally just the transitions that people were using. Now, back to my point why I said, R has some benefits here. So one thing is you can literally write down the attention, directly from this formula, and it's exactly this, right? So we're just saying we take the x, we take the end point, which is the last one. So this is this guy, right? Then we have the WQ. Then we have X again. We have WK. And then here, we're transposing it. Then we have V. So that's this part. So that's the value part. And then we just compute the softmax. And then we have the prediction, which is just the softmax of that, right? So this is really nice that you pretty much can directly write out what you're trying to do. And the reason I'm showing this is not because, well, in reality, and I'll go back to this, but in reality, there is actually an implementation in Torch that does the whole attention piece. So you could have done it that way. But using it this way has a couple benefits. So one of them is you can just put browse in there. You could put breakpoint in there. You can actually inspect the data in the middle of this. So that means as the algorithm's running, you can say, okay, I maybe have some conditions, and if something gets out of whack, I want to have a look at it. You can do it, and we're back to the interactivity. So you could go in there, and you kind of start looking at the matrices. You can start plotting them. You can start figuring out how does it match to my original data. So you have all this power of R at your fingertips, essentially, even in the middle of a fitting neural network model, which is really nice. So that's, and there are two great packages that this is based on. So it's the Torch and Luz packages that allow you to do that. So like I was saying, well, once you get beyond the stage of figuring out that everything is fine, yes, you can optimize it. You can maybe replace that attention piece with with just one call to torch that makes it faster, but you lose that ability of interactivity and looking into things internally and so on. So just let's talk a little bit about the results here. So what we did is so what I'm going to show is the result of running the model just the way you would run an LLM. So you start with some couple locations, and then you start predicting the next one, and the next one, and the next one. I mean, I'm sort of cringing as a statistician, right? You're predicting something, and then you're predicting based on the prediction, and then you're predicting on prediction of the prediction, and so on. But for some reason, this seems to work, okay? So that's all we can say. Like, it's like the LLMs, right? And we are evaluating on the holdout set, which means it's a data the model has never seen before, which, again, we sort of expect the models are really bad at that, but we'll see. So what we're doing is it's kind of hard to measure accuracy here because the problem is that the trajectories can be of different length. You know, they can stop at a certain point. And so although the model doesn't know how far these things are from each other, we actually do because we do have the graph. So we'll be using the graph to compare how far off was the model by looking at the hop distance. So, you know, how many nodes from, how many nodes are there between the two predictions? And that way we can at least find out sort of how good are we. And the other thing to note is that there is a bit of a problem in the sense that, you know, the trajectories are not unique. So if you start somewhere and go somewhere, they can be actually different people giving to slightly different direction, different locations. So we essentially just say, well, look, we can just only average out of this, which means the model may be right for one of them, but it may not be right for others. So there's not much more we can do about it because, you know, the starting set is fixed. But I'll go into that a little later, what else it means. So this is what the results look like. So that was sort of shockingly to us. The results are pretty good. So this is in essentially the hop distances. So we do have some outliers. There are some really bad results, but it's very, very few. As you can see here, most of them didn't have sort of a hop distance worse than, let's say, 1 or 2. So the reason why I have two numbers here, actually, I should explain that, is that because of the lengths, right? So if we stopped early, so there are two ways to look at it. You can say, well, we just take the endpoints of both trajectories, and we look at their distance and their hop distance. And so that's the max. It's sort of the maximum length. The minimum length is sort of going, well, if one of them stopped, at that point, we're comparing the two trajectories, seeing, you know, how well did they match. So and I'll show a couple of examples to explain sort of what it means. So here I have one example. So the black polygons are the starting ones. And then essentially I'm using red and blue, and then I'm transparently overlaying them, which means the pink ones is where they both agree. And then our prediction stopped here, and the actual trajectory stopped here. So this is sort of a pretty reasonable, you know, good case. It wasn't complete match, but it's actually, so in the min distance, we would have 0, and in the max distance, we would have 1, because it went further that we didn't predict. The couple other examples, just to give you an idea. So here is someone starting in really rural area here, and then going up north, and the trajectory was perfectly matched. The problem is, if we get exactly the same starting point, now, I don't know if you can see that little change, so I've flipped between the two maybe. So this is one, this is the other, and you just look here. So, oops. So what's happening is that, wrong direction. So one of the trajectories in the second trajectory actually stops earlier, and the person, you know, turns left, so to speak. But because it's the same starting point, you know, we can't really distinguish these two, or the model can, you know, distinguish these two. And here is one more that's sort of showing where we really diverge in the end. So there's a lot of matching ones, and then one goes, the real person actually goes, the real person goes to the CBD, whereas the model says we should go to Newmarket. So one thing that really surprised us actually that the model performed really well, given that we didn't give it any information other than the actual data. This is sort of like going back, it was reminding me of the Netflix prize time, where, you know, remember the Netflix prize, where a prediction of movies, movie ratings. And the thing was that originally there was all this metadata, right, about the movies, like, you know, what's the author, what's the content, well, who's the director, who are the actors, all this cool information. that turn out to be completely useless. Because in the end, you just look at collaborative filtering, just using the ratings of other people, and you have much better results than anything that you actually give it to the model. That sort of reminds me of that. It's like, well, just look what's happening, and it gives you much better predictions than if you try to add all that information in. Which is kind of surprising here because, we know these are hard constraints, right? We know that you cannot go from here to here, but the model figures it out and never does it, so it works as well. The other thing is, which is kind of cool, is because, as I was saying during the attention piece, that we actually do have the probability. So that means we just picked the highest probability. But for example, in the case where there was this diversion or someone stopped there and other people went straight through, we can just sample from the distribution, right? And we can just get the distribution of the trajectories. So we didn't do that, but we could, and we hope that if we build on top of this, that it should be possible to see, how well do the distributions match, as opposed to just looking at the individual trajectories. The other thing is that it's something we did, but I didn't want to show the information because it gets more complicated. You can actually add additional informations to the model, which the way you do it, you just add extra columns with your information, like, for example, time of the day. So we did sort of morning, after, evening commutes. And all you can do is you just add an extra layer that just adds that information onto the rest of the model that we already have, and that's it. So it becomes really easy to just add additional information, and you can, anything you can sort of think of that you can encode there. So my comment here is, I think it was really useful to do that in R. I know that people are saying, oh, you have to code all these things in Python. So no, you don't, actually. There are now really cool packages out there that allow you to do these things in R. And for what you get is interactivity and graphics, right? So we can now interact with it, we can inspect it, we can look at it in the middle of essentially doing all these things, which is really nice. So that's sort of one point. So this was one idea where it was saying, well, let's do something that has to do with LLMs. Essentially, I built this way, so let's do it this way. The second use case I want to talk about just briefly, because it's we just did it, we're talking weeks here, is the idea was, well, there are all these LLMs, which is pretty cool. And one side effect of them is that they allow you to do embedding of documents, or actually it's beyond documents, but for now, let's just say for documents. Because that's how they start, right? They first embed the entire prompt, and then they start running it through the prediction. So what about just the embedding itself? Now, we know there have been sort of chunk-wise embeddings, word-to-vec, BERT, and so on. So these are cool, but they're usually sort of based on a chunk if you want to do queries, and I'll talk about this in a second. But what about saying, like, no, let's not bother with it. Let's just embed the entire document, because we can, right? Because we have now models with 128K and larger context windows, which easily fits any paper. So the idea was, well, let's take the R journal articles. So, since we are, our foundation, we are the publisher of the R journals, and they are open access, so it's really easy to actually just get all the sources from them. So we can just run them. Let's just embed them as they are. Don't even bother even processing anything. And then what it does is we get these high-dimensional embeddings, and so we get distances. So we can start looking at distances between papers. And not only the papers we're embedding, we can actually also embed queries. We can embed, let's say, new documents, and we can just compare how do they work. So some use cases, as an R journal editor, it's really hard to do things like, assign keywords. So people assign their own keywords, but they're usually pretty bad, or they don't do it at all. So the problem is, how do we actually fix that problem? Have a better solution for it. So we could do this, right? We can look at what's the distance between papers, sort of where do we think would it fit the best. The other thing is, and something that I have to talk to the editorial board, we didn't actually do it, but it would be cool to do, is we could do things like matching reviewers. So, if people are reviewing certain kind of papers, it's really hard. We do have sort of list of reviewers, and this is a call, please, you can just go to journal.rproject.org, and you can become a reviewer, and we need reviewers because the number of papers is constantly increasing, so please do that. So matching reviewers to papers, because again, same thing, the reviewers provide some keywords sometimes, and then we try to, that's the best way we can do at the moment. I mean, of course, there are other ways, looking at what the citations are and so on, but all these things we could automate much better if we could have some kind of distances between people, or what papers people wrote, or what people, how the papers match in there. So this is what I'm going to use is just a local model. So now Hadley said yesterday, don't bother about small models, which is true for all the chat stuff. But in this case, we're really just trying to say we want just an embedding. So it doesn't have to be the greatest and latest. So here I'm just using Gemma 3. And this is a tiny little package, Lamar, which is just a really thin wrapper around Llama CPP. So essentially, it's just local. Doesn't use any API calls or anything. It actually literally embeds the model in R, so then you can interact with it. So we can set the context window. So in this case, I'm just picking 1600, but you could actually pick whatever you want, as long as it fits in your memory. And in this case, I'm just saying I'm going to be doing mean pooling, and we'll talk about that in a second. So essentially what it means is that the result will be one vector that's exactly the same length as the embedding that this model uses. So in this case, in Gemma, and for this Gemma, it's about 4,000 entries that we get. You can check, you can actually tokenize the input and see how many tokens do you get out of that article, and you can just get the embeddings out of it. And it only takes a few seconds. It's like 3 seconds or something like that. So just for the fun of it, I figured I'd just show you the raw embedding. So this is before pooling. So I just took one abstract, one of my papers actually, and then and I just run the embedding on it. So you get a full matrix. So for every token, you get the full 3,000 values of the embeddings. And it's not like this is supposed to be meaningful, but just so you get an idea sort of what does it look like. So these are 3,000 lines through there, as you can probably tell, or almost 4. And all the 200-something tokens that we had in that particular abstract. So that kind of gives you an idea. But what we're getting out of it is, with the mean pooling, we're just pretty much just taking mean out of this. So if we apply all of that, it's kind of hard to assess, how well we're doing, how useful it is, because we don't have a ground truth here, right? We're just trying to say, hey, these are the different distances. So one thing I did is said, well, let's look at the keywords we have. So this is a good projector. It's good, so you can actually see the gray points. So the gray points are either papers we don't have any keywords for, or where they were sort of one of the keywords not from the main categories that there were enough of them. So I just wanted to make it more so that we can look at it. And you can see there is sort of some structure to it, right? So and then I use multidimensional scaling to take the distance matrix. So just taking the cosine distance and then just looking at the essentially the multidimensional scaling of the distances. So you can see there are groupings. So we have reproducible research here. Now, one thing you have to keep in mind is that this is not a disjoint set, right? The paper can actually flag multiple categories or multiple keywords. So it's not like we would expect complete separation here, because let's say if paper was just on reproducible research, sure, they should be in the same area. But very often people use keywords where they say, so for example, I don't know, like half the papers actually say graphics because they have a plot in the paper, right? So it's not quite helpful, because we'd rather know if they actually do something about work in graphics, but hey, what can we do? So essentially, so here are the reproducible research ones. If you look at distributions and multivariate statistics, we're kind of more in this region. We have, so graphics and visualization, as I was saying, is kind of spread out, but you do see it's close to, let's say, reproducible research, because very often you kind of deal with that as well. And use the same frameworks for reproducible research as for graphics often, because things like our Markdown and Liter and so on kind of allows you to do graphics, which you couldn't without it, and so on. So it kind of passes the smell test. So now we want to go forward and see if we can apply this. And I did look up some, like I just pushed in one of my papers that's not in the R journal and looking like what are the closest papers in the R journal, and it was, sensibly was about the same topic. So that seemed to be pretty well. But that's all. It's not very qualitative, I agree, but we need to have some kind of next measure or next application to see if we can say how well we're doing. So, I want to talk to the editorial board and see how can we use it for, let's say, matching incoming articles. That's another issue. So when people sometimes submit very similar paper to what they submitted before, so we kind of could see that, and that way we can link it with the old paper. It's not that we don't allow you to do that. We want to know which paper this is this was essentially next version of. Suggestions, some navigation maybe. And if we went beyond just these embeddings, we could sort of combine with other like retriever augmented generation approaches for things like search on the web page. So there's a lot of cool stuff we could probably do, but that's probably for later part. And then of course we could extend it to other open access journals, so we could embed other articles and compare that to ours and see how it goes. So before I finish, I actually want to talk a little bit. So I was talking about this special case where we're really just using full embedding of the entire document using the embeddings from the LLMs. That's usually not what you do if you're looking for things like retrieval, because you want to actually know much more closely, this is the section, this is the part of the document. So there are really cool tools for that. So I just want to shout out to these packages that are available. And they are much smaller models than you can use, so you don't have to pull in a full Gemma to do that. You can just use BERT and so on. And so there are packages to do that. But the idea there is, though, that you have to chunk up the document into smaller pieces, and then you can embed the individual pieces, and that means you actually get many more embeddings for a single document. But you can search in them and say, this is where the match is, and you search, and you can then combine it with a whole chatbot that you can essentially say, hey, I'm looking for a paper on this and this and that actually goes back, does the RAG, pulls out the paper, gives you the result. Michael, I think, will be talking actually here. So I just saw his work on the JSM, and so I think kind of wraps up a lot of this into one. And then there are packages that do embeddings in this sense, meaning in the chunkwise sense as well. So we can look into those as well. So in the end, so I'm circling back, essentially saying, well, I hope I was kind of making the point that R is a data analytic language, which is for interactive use as essentially an orchestrator or conductor of all these other tools as well. So that's what I sort of want to make the point, why I don't think that the other languages will be eating our lunch, because that's not what they do. They're meant for a completely different purpose. And very often you see that when you talk to people, if people come from the other worlds, then they say, oh, you guys are not gonna, what are you doing here, right? Whereas if people come from the R world, and then they use other languages, and it's easy, we learn languages all the time, right? So that's not a big problem. But then you say, oh, this is so painful in this language, because it's not a data analytic language, right? So you can do things, it's just not as a friend of mine called it, ergonomic, right? So it just takes you a lot longer, it's much harder to do that. You can do it, but it just doesn't feel that easy. So R is really specifically, has been targeted to do data analysis and for the sort of interaction with the data, and not writing code or writing specific tools. So we are focusing on what do we do with the data, and we defer to how to. Hopefully someone else wrote a smart tool to do that, or maybe in another language, it doesn't matter. But that's sort of what R is really good at. The other thing is the R package ecosystem is absolutely crucial for this, because that's what makes it so powerful. If we just had the language, then we could only do sort of basic statistics, and okay, we get graphics, it's fine, but then we wouldn't have the entire world of all the different tools and new approaches and so on. So all the things I was showing are just packages that are beyond the base R. So in base R, we're really trying to just keep the sort of the base, as it says, running, and then you just add all the other things to it. And that's, I think, which is really important. So I'm saying, just go out, write packages, think of new methods, just do it, and then everyone can use it, right? Because the language is what binds the data to your tools, what you will be creating. Here are just the examples of what I was using here. All right, so that's it. Thank you very much. So we're acknowledgement. So this was work with, as I was saying, with many other people that were involved in this. I'm using the Grapehopper project, OpenStreetMaps for the routing, Torch packages for the attention stuff, and this was some of my collaborators and students that were working on the New Zealand safety stuff. So thank you very much for your attention.
All right, Simon, that was fantastic. Thank you. Just like yesterday, go ahead, scan the QR, enter the code if you have questions. We've got a couple in here already, one of which I wanted to ask, which was related to the first vignette that you shared. about your decision not to include any spatial information in your attention model. And so, of course, LLMs are going to learn relationships between words and distances between words. But one of the unique things about your use case is that you might not be able to physically transit from area 1 to area 3 because there are no roads between area 1 or 3, or you would need a helicopter or something like that. So tell us a little bit more about that decision and what you think encoding some of the spatial information into that model might provide in the future.
So, you know, we were sort of thinking, well, let's see, right? I mean, how does it work out? We're not giving that information to the model. But because of the fact that the model seems to be really good at actually figuring out that you can only transition between essentially the last point and the next point. You cannot transition between the other points that you see, which is kind of interesting because it's really not encoded implicitly anywhere. But really in the entire evaluation, we didn't actually see cases where the model would be using some, you know, implausible transition. So that was also surprising, right? We started, to be honest, this started as essentially like this fun project thinking like, you know, let's see. What can they do? And we did have some, you know, bad experiences first because it actually really is important to see how are you going to encode your data, because originally we just tried things like, oh, let's predict more than one, you know, the statistical way, right? You see, okay, this is my X, this is my Y, so let's predict 5, right? It was terrible at that. What we actually learned was the structure of our training data, which is meaning like how did we try to train it? You saw these triangular, structures that we were feeding it. So it learned the triangular structure, but it didn't learn the locations. So it was kind of fascinating. But once we went to this sort of one at a time, it worked beautifully. And I suspect it's because we're really focusing it on like, well, make sure the next one is correct and is sort of the one that comes. So so in some sense we were sort of surprised, pleasantly surprised that, you know, it's the same thing with the LLMs. Like we're not really giving him grammar of any languages or anything like that a priori saying like, you cannot do this, right? We just tell them, well, this is what people use, and now come up with something, you know, similar. And it seems to be working in this case as well, where it's saying like, well, this is where people went, and, you know, so this is where you go. Now, obviously, I wouldn't expect it to go, even though we did have a holdout set. I mean, I don't think, so I didn't actually look at all the ones with bigger distances, but you would expect that if there is some kind of route that was never taken somewhere far away, that's not part, even as a sub-route of any other one, then I would expect it to fail, obviously, because it hasn't seen this before. It's the same as with the collaborative filtering. There's the cold start problem that if you have a new show, you cannot look at what people, you know, whether people watched this show before. So it's the same issue here. But you know, it seemed like actually it doesn't need the spatial information to do perfectly well in the predictions.
Interesting. There was also one related follow-up question, which is how do you handle in that case the commuters who work and live in the same SA?
So that's a good question. We excluded them. So because we can't, you know, there's nothing we can do with them because we don't have any locations, right? So that's a very good question. So they are people that, you know, work from home, but yeah, there's no point in computing a commute for someone. And you're right, I mean, theory that you could even have someone that, you know, like walks a block away, but it's fairly rare because of the fact that, as I was saying, firstly, the SA2s are sort of proportional to population roughly, so they get really smaller the moment you get into denser areas. So as you saw maybe a little bit in the central city and CBD, actually it's like tiny little things. So it means you're not likely to see that, oh, you know, unless you really work from home, you're less likely to actually be in the same SA2. So in that sense, but you're right. I mean, there's nothing we can do because there's no information that we have.
Sure. Okay. We're getting close to our coffee break, so two maybe quick final questions. So the first is, what do you think of vibe coding? Real question from the audience. What do you think of vibe coding?
I don't know.
Okay.
I have I have no opinion.
Okay. All right, and then the final, very quick follow-up. There's a young, eager, soon-to-be or hopeful to be PhD student. Can you please explain the softmask function?
So essentially, it's a multidimensional version of the logistic transformation. So essentially, it's the same. It's just across multiple columns. That's pretty much all it is. So it's really just a generalization of the univariate case. So.
Impressive. That was softmax in 15 seconds. So let's thank Simon. There's more time for questions right after this. We now